Okay, here's the PowerPoint that I wanted to do in class earlier. So I'm going to combine sections 2 and 3. I don't know how much of this you heard before, so I'm just going to go through it again. In this chapter, again, I think hopefully you heard me say it's sort of like the home stretch. I mean, all we have left to do in the Calc 1 curriculum is integration. So one of the main applications of integration is finding areas, all kinds of accumulations, but mostly areas. So some areas can be found with techniques you already know, if they're known shapes. If you can end up graphing a circle, a semicircle, a quarter of a circle, a triangle, a rectangle, a trapezoid, then you can use your geometry formulas to find those areas. If they are irregularly shaped, if you just have some, boundary from a curve and some other boundary from another curve, then we're going to be able to use calculus to, well, actually, just, basic math with rectangles to approximate the areas. And then we're going to bring in calculus with limits to turn these approximations into exact answers. Okay, if you care to pause on this, you can read all about Riemann. We're going to talk about Riemann sums. If I don't explicitly, call them at any point Riemann sums, you'll see abbreviations, things that look like find R5 or find L4. And R doesn't stand for Riemann in this case. It would stand for rectangles that have right endpoints, or these would be rectangles that have 4 endpoints. These would be 5 rectangles, this would be 4 rectangles. So we'll get into Riemann sums in a little bit. But all of these basic ideas, and here's where it says Riemann sum right here, all of these basic ideas are connected. So what I want to do today is just concentrate on the easy stuff for us to get started. So I just want to concentrate on the example 3. And we're going to do each one of these. I want you to understand how, given this, so I guess first I'll explain the notation, and then we're going to sketch a region that corresponds to this thing. This is called a definite integral. And then we're going to evaluate it just using geometry. So you would read this: the integral of 4 dx as x goes from 1 to 3. All it means is what is the area between this function, the function y equals 4. Over here we'd have y equals x plus 2. Over here we would have y equals the square root here. So what is the area between that graph of that function and the x-axis? Alright, so that means I want to graph the function. If I want to graph if I want to graph y equals 4, then that is just a horizontal line through 4. Alright, so that's that as a function. This means these two things here, this is called your lower bound and that's called your upper bound of your definite integral. Those are just the x values that we are starting at and going to. So we are starting at, pick the right color, so we're starting at 1 and we're going to 3. And so what does that form? Well, it just makes a rectangle. So again, this is the area. These things mean the area between the x-axis and the given curve. So again, in this case, it's just this. That is just a rectangle. That is from 1 to 3, that's 2. From here to here, that's 4. So that's a rectangle that's 2 by 4. And that answer is 8. How? Why? Because it was just a geometric figure. That was just a rectangle. So if we want the area of a rectangle, we just take the base times the height. Okay, let's try another one. Now we want to find the integral from 0 to 3 of x plus 2 dx. Alright, so we just want to understand this as an area. This is the line that has a slope of 1 and a y-intercept of 2. So I'm going to do my y-intercept first. and then since my slope is an understood 1, then I'm going to go up 1 over 1, up 1 over 1, and I'm going to do that as many times as I need to. And this line does do this. But remember, I only want to concentrate on the area between this function and the x-axis from 0 to 3. So from 0, 1, 2, 3 to 3. Alright, so this is what we're looking for. Again, it's just geometric shapes. So you can look at this as a trapezoid and do 1/2 times the height times the sum of the bases. If you kind of turn your head sideways, you would see how this could be the height, and then these could be the bases. But what I'm going to do is just chop this up. Here's a rectangle that's 3 by 2. So that rectangle is 6, base times height. And then this is 3 by something, so its area is going to be 1/2 times the base times the height. Now we just have to figure out how high this goes. To figure out how high that goes, just put 3 into the function. So 3 plus 2 gives me 5. So I guess this isn't that great to scale, but that means that this went from 2 to 5. So that was also 3. Okay, it went from 2 to 5. So this is 1/2 times 3 times 3, or 9/2. And then I want to add together the area of the triangle plus the area of the rectangle, and that would be 12/2 plus 9/2 gives you 21/2. And you do normally see these as improper fractions. Okay, last one. I'm not worried about rushing or asking if you have any questions, because you could always pause it, right? If you can't work through any questions you have, just send me an email. I'll check throughout the night. All right, this last one, this is harder for people to realize that, hey, I do know what this looks like. So if you set this equal to y first, and then you say, well, I don't really know what that looks like, so let me see if I could make it look familiar. So let me square both sides. Then you get y squared equals 4 minus x squared, and then finally you can throw that x squared over to the other side, and you get x squared plus y squared equals 4. So I'm going to tell you what it looks like in a minute, or I'm going to draw it, but if you want to try to remember what that looks like and you don't think you're quite there yet, then pause the video, because I'm going to do it now. That is a circle with radius 2. But this is the whole circle with radius 2, where if I took and I solved for y, if I went backwards from here and I solved for y, I would technically get y equals plus or minus the square root. So if you take the positive square root, like we have here, ignore those squares, that's the top half. If you would take the negative square root, that would be the bottom half. Alright, so I just want the top half of that semicircle because that is a positive square root. So that's what the graph looks like. Alright, where do we want the area from that curve? Between negative 2 and 2. Well, as luck would have it, that's where this is. The only bounds you'll see for right now, until you learn more integration techniques, is this will either be negative 2 to 2, or it'll be 0 to 2, or it'll be negative 2 to 0. You'll only have to find a whole semicircle or a half of a semicircle, which is a quarter of a circle. Those are the only possibilities you'll have right now, because here you could say, oh, well, that area is going to be 1/2, I should say area, is 1/2, because it's a half of a circle, times pi r squared, because the radius of this circle is 2. So that's 4 pi, and that's a half of 4 pi, so that's 2 pi. So that integral value is 2 pi. Alright, next. I think these problems here come from 5.3. Like I said, I'm mixing them up only because I want you to understand just sort of the natural progression. These are things that you already know how to do. I actually want to take an adjusted number 34 to do with you for an example. Meaning, I want to give you a value for A to make this more concrete. So we're going to do, get a little thing here. We're going to do negative 4 to 4 of 4 minus the absolute value of x dx. Alright, so the key here is for you to be able to graph this, preferably with a calculator. If you know that the absolute value of x looks like this, then you would know that the negative absolute value of x looks like this. And then finally, so what does the 4 do to it? It takes the negative absolute value of x and it shifts it up 4. So I am going to draw that graph, and I want to make sure that I'm seeing this from negative 4 to 4 on my x-axis, and it happens to cross at negative 4 and 4. How would you know that? Well, you can plug them in. What do I want to do here? You could plug in negative 4 right here. Absolute value of negative 4 is 4. 4 minus 4 is 0. So that's 0. That's at negative 4, 0. Similarly, if you plug in a 4, you get 4, 0. Alright, so what do I have now for a shape? Well, I just have a big giant triangle. So this area is 1/2 times the base. You see the whole base is 8, right? Times the height. And that's half of 32, which is 16. Alright, so anything that you get in 5-3, you can just draw all of these. This is a line, that's a horizontal line. These are, absolute value graphs turn into triangles. These are semicircles. So that's how they expect you to find those areas. Alright. If we have one of those irregular shapes, that's what I was talking about earlier, say like this shape here, the pink region in this graph, that's what they want you to find the area of. Well, how could you find it? Right now, you don't have a geometric formula for this. So you can try to put some rectangles in the picture. All these rectangles happen to lie below the curve, but they all touch the curve somewhere. Like I'm leaving this little, laser pointer on the pen where the rectangle does touch the curve. So if you knew what all these x values were, you could just plug the x value into the function to get the y value, and that would give you your height. Here, we're using a similar process, but the y values cause these rectangles to all be above. So this is called a lower sum. This is called an upper sum. The notation for a lower sum is little s of n, or sometimes you see this is a subscript little s sub n. And then the notation for an upper sum, which is where all the rectangles lie above the curve, is capital S sub n or capital S of n. Instead of lower sums or upper sums, you can have a mix. Let me make sure you realize that this curve could have then done something like this. You can make, so these are inscribed rectangles, but we can also say, we can make this so that they are left endpoint rectangles, because right now this rectangle touches the curve on the left. This rectangle touches the curve on the left. This rectangle touches the curve on the left, and so on. And we can keep making rectangles that always touch on the left, but they don't always have to be below the curve, because you could see pretty soon now all of my rectangles that I'm drawing that touch on the left, these lie above the curve. So don't worry too much yet about lower sum versus upper sums, or left endpoint rectangles versus right endpoint rectangles, until maybe you get to a problem where you have to approximate that. But I just want you to realize that you can use areas of rectangles, which are all just base times height, to estimate the area under a curve. Alright, To get an exact area under a curve, it's going to help if we have a few extra tools in our math tool belt, and one is this notation. This is called summation notation. So let me guide you through each piece of this. This is called sigma, and that is your Greek capital S. It means summation, and it means that anything that you're going to get from this, any information or numbers that you're going to get from this here, you're going to have to cycle through from this lower bound to this upper bound, and the sigma means you're going to add them all together. So that's why this is summation notation, because this indicates that you're going to have a sum. The 1 is called your lower bound, the n is called your upper bound, and this is a function of I. A sub I is just a function of I, because I is what's going to change. So let's say like n is 7. Then we're going to go through this and we're going to start at 1 and say a sub 1 plus a sub 2 plus a sub 3 plus all the way up to a sub 7. Okay, and that's what summation notation does and means. So here are some examples. I think these are from your book. First, I just want to look at a nice simple one, number 4. Okay, so for this, just look at the, one thing that I didn't mention in the other one is your index of summations. The indices of summation, they're usually I or J or K. That could be any letter, but typically they'll stick with I, J, or K. That means that that's the thing that's going to cycle through all the integers that start here and end here. Alright, so we have the summation of 3 over J as J goes from 4 to 6. So that means the first number we're going to plug in for J is 4. Then we're going to add a 2. The next number we plug in for J is 5. Then the next number we plug in for J is 6. And I'm going to pause this and do that on my calculator. Okay, so that's 37/20. And you can use your calculator to get any of these sums. What did I want to look at next? So there's a problem back here, and it's number 5, that says the summation of C as K goes from 1 to 4, where this is a C and this is a K. I want to guide you through that, and give you sort of 4 similar problems here. So if I had the summation of 3 as I goes from 1 to 4, that's almost like that one. Notice that this has an index that's supposed to change, and it's supposed to change from 1 to 2 to 3 to 4, but I don't have an I in this function. This is a constant function, just like you can have, y equals 3x, or you could just have y equals 3, and those graphs would look very different. So I'm going to keep track in my head. I equals 1, now I equals 2, now I equals 3, now I equals 4. So I still am adding, this function, and I'm doing it as I starts here and ends here, but it's just giving me 3 plus 3 plus 3 plus 3. Alright, so think about what's going to happen here. And this is where, I had these written on paper. I was going to do these with you during class, and I was going to ask somebody, so what's a shortcut here? Because I don't think anyone wants to write out, 14 threes, right? But isn't that the hint right there? You would be writing 14 threes. If you're going to write 14 threes, then you could just take 14 times 3 and get 42, right? So then a shortcut for sort of any of these problems, if I do want to write out 14, if I want to take the summation as I goes from 1 to 14 of C, that would be C plus C plus C plus C 14 times, so that would be 14C. And then that just brings me to, you can, so the answer to number 5 would have been 4C, because I think that was the summation of C as I goes from 1 to 4. So that gives you a general formula for this. Pause this if you want to write it down first, because you don't need me anymore, because you figured out it's that. Or you might have written NC. It doesn't really matter, right? So you're just going to write out n c's, so that's n times c, or c times n. What that brings us to is a formula, because before we get to the formulas, why would you want a bunch of summation formulas like you're going to have on the next page? Well, because otherwise, look at what we would have to do here. To get this summation, and this is something that you would sort of be expected to do sometimes, but what are you going to do? Do 1 cubed minus 2 times 1 plus 2 cubed minus 2 times 2 plus 3 cubed minus 2 times 3 plus, and you're going to do that, I don't know, until you get to 25. So I would guess no. Whether, you know, it's a lack of patience, lack of time, whatever. So this is one way that you could find this answer, but that's not the intent. There are shorter ways to take care of this, and they come from these formulas. So you should pause the video now and write down these formulas. I will talk through a little bit of it. This is a property where if you have, say, like a number 5 times your function, you can pop the 5 to the outside. Okay, just like you would with derivatives and just about anything else. I always say it's a coefficient, it just hangs out. If you have a summation of a sum, you can turn that into a sum of summations. If you have the summation of a difference, you would turn that into the difference of two summations. We're going to use these properties so that we can use these formulas. Now you just derived this one. The summation as I goes from 1 to n of c is cn. We just figured that one out. If you have the summation of I, there's a cool way to prove this. There's a cool story behind this, but I'm already at 21 minutes. I'm not telling you a story. You know, Google that maybe. There's a formula for I squared. There's a cool proof of that on YouTube, and but it involves a little bit of calc too. So, and then lastly, there's a formula for I cubed. So write those down in your notebook before you go on to the next problem. Alright, so I'm going to use those to help me get this answer so that this summation doesn't take me forever. I'm not going to do what I started on the last page. Now I'm going to use the properties, so I'm going to split this up into the sum of I cubed minus the sum of 2I. That was that second property. Alright, next I'm going to use the first property on the second piece of this, where it says I can take the 2 because it's a coefficient, or yeah, it's a coefficient, and I can pop it outside. So I'm going to say minus 2 times the sum of I. That says 25 up at the top for the upper bound. Okay, now I'm going to use the theorem. The theorem says that the summation of I cubed, as I goes from 1 to n, is n squared times n plus 1, quantity squared all over 4. It says that the summation of I is n times n plus 1 all over 2. So let's do it. Let's write this summation, the summation of I cubed, as n squared times n plus 1 squared all over 4. You see where I got that? I got that from right here. Okay, then I'm going to say minus 2 times, now I'm going to do my summation of I. My summation of I is n times n, whoops, I'm not using n's though. My n is 25, so 25 times 25 plus 1 all over 2. And I'm going to do almost all of this on the calculator, but I don't know. I just sort of feel the need to simplify a little bit where I can. Like I can cancel those 2's. I'm kind of tempted to make this a 26 squared, like a 26 times 26. I guess I'm not just tempted, I guess I'm doing it. And then I'm going to cancel the 4 here and make it a 13, cancel the 2 with that. You know what, I would do that, but I think that's just going to make it more difficult for you to understand what I'm about to do. So let's just use the calculator, since we're going to go to the calculator anyway, and figure this out. So I'll pause this so you don't have to wait for me to use my calculator, and you use yours and come up with the answer for this. Okay, so what I typed in was 25 squared times 26 squared divided by 4 minus 25 times 26. And that's what I got. And that's why you need those summation formulas. Okay, what comes next is we want to add a limit process to this, what we just did, so that we can get an area under the curve. But I will wait and put that up as a separate video because I was going to wait and do that in tomorrow's class. I am also going to try to have a class tomorrow in Blackboard again. If I can try to figure out how to hardwire my laptop so that straight into the router, I guess basically if I can find a cord, then I will hardwire into the router and I shouldn't have to worry about my Wi-Fi signal. Okay, I will put this up now and I'll look for my emails if you have any questions.